And so now what we're doing is we really are starting to talk about what's going on inside of an atom. Up to this point, we've used this little model, the little model of a dot, to represent the atom. And I mentioned to you that, okay, that's a fine model. And we talked about atoms being the smallest constituent of normal matter. And we put the word normal in quotation marks because there's certainly matter that's smaller than an atom. And we're going to talk about that today. But the first thing that I want to do is preface this by saying, this is the time that you need to start thinking about memorizing formulas. And specifically, it's not going to be until the next section that we really get into memorizing a lot of different formulas and names for polyatomic ions and other ions and things like that. But it really is important to start now, because once we get into that next chapter, there's going to be a lot to learn. So we want to get into this practice now. And so with that in mind, you should probably do this. You should definitely know the name and formula for the first 30 atoms. And let's just start there. That's a good place to start. There's going to be some other formulas and names from the periodic table that you have to know by heart, but this is a good place to start at the first 30. There's not going to be that much more. We probably will only add another 10 or so to the list, but they won't be in order on the periodic table. And so I want to just go ahead and let's start with the first 30 from the periodic table of elements. And what I mean by that is, if I give you this symbol, then you should be able to say that that's oxygen atom. If I were to give you the phrase fluorine atom, then you should be able to say the symbol for that is F. And so that's what I mean by this memorization. You don't need to memorize the atomic number. You don't need to memorize the atomic mass, any of those other things. All you need to be able to do is go from a symbol to the name, and from the name to the symbol. And so let's go ahead and let's get that in your notes, get that as something that you should get going. Let me say one other thing about this bit. What I'm talking about when it comes to memorizing symbols and names, this is called nomenclature. And when we're dealing with nomenclature, it is essentially straight memorization. That's all there is to it. And I want to make sure that students realize that if you don't do this memorization, not only will you perform very poorly on exam 2, because exam 1 will cover sections 1 through 4, but not section 5. Not only will you do very poorly on exam 2, but essentially you won't be able to solve other problems, because other problems will assume an understanding of the nomenclature. And so students don't realize often until it's too late that just saying, forget about it, I'm not going to bother with nomenclature, is basically saying, I'm going to retake this course next semester. And so I just want to make sure that I say that. If you don't bother to know the nomenclature, make sure that you sign up for this course early so that you can take it again in the spring. It's really that important. That's how central it is to the class. So the question is, are you going to give us the 30 that you want us to know? So when I say the first 30 atoms from the periodic table of elements, I want numbers 1 through 30, and they're numbered on the periodic table. So go to the periodic table, find the numbering scheme, and know the first 30. Alrighty then. All right, and so what I want to do is I just want to talk a little bit about the internal structure of an atom. And so let's talk about hydrogen. If you look, and I'm going to draw a fake periodic table, kind of looks like this. And if you look on the periodic table, you'll see that hydrogen is number 1. And so that means something. And we're going to talk about what that means in just a second. But before we do that, I want to establish, well, what is actually inside of an atom? This is an okay model for the hydrogen atom itself, but what if we want to look closer inside the atom? Well, it turns out inside the atom, and this is going to be a really overly simple picture of what's going on. Inside the atom, we have something called subatomic particles. And maybe you already know what the 3 subatomic particles are, but they're the proton, the neutron, and the electron. The proton, neutron, and electron. If we look inside the hydrogen atom, what we find is we find 1 proton and a tiny little electron outside. And I'm at this point in the game, since this is introductory chemistry, I'm going to go ahead and model the electron sort of in an orbit. Even in introductory chemistry, we'll learn later how the orbit is actually the wrong model. But we won't do that until later. And so for now, just like before, it's a chemistry lie. The electron isn't really in an orbit, but it's okay to look at it that way for now. And so that helps us tie the 2 models together. If I think about the dot that is this model of the hydrogen atom, and then I start to zoom in on it, then this is what I'm looking at. I'm looking at an atom that has, or the new model, the orbital model, involves a proton in the center and an electron on the outside. But what happens if I start to get into some heavier atoms? Let's think about helium. It turns out that helium has 2 protons, 2 neutrons, and it has 2 electrons in an orbit around the atom. And again, the orbital model isn't the best model, but it'll be fine for us for now. This is what we're going to look at when it comes to a helium atom. Let's do a little bit more specific defining. I want to define what this proton and electron and neutron are, because they have some properties. Let's start off with the proton. It turns out that the particles inside the atom are quite different. The Proton and neutron happen to be the heavy ones, the ones that carry most of the mass. And the proton and the electron happen to have all the charge. And so what I want to do now is I want to define these particles in terms of their properties and what they do for the atom. And so let's do that now. So the proton is a subatomic particle that identifies the element. And it identifies the element by atomic number. And what I mean by that is that the atomic number, and this is the number from the periodic table of elements. So when I told you to learn the first 30, I mean the first 30 in atomic number. The atomic number equals the number of protons in the atom. The proton has a charge, and the charge is +1. So what does that mean? The value of the charge is equal to 1, and the flavor of the charge is positive, right? So charges come in two flavors, positive and negative, and the flavor of the charge is positive. The mass of the proton, although it's really the most massive particle, and protons and neutrons are the massive particles, it's really tiny. It's 1.67 times 10 to the negative 27 kilograms. But I think at this point, we're already we don't want to deal with that. That's too small of a number. So that's like 0.00000000000. Oh, I already lost count. So let's not use kilograms. Let's invent a new unit. Let's call it the atomic mass unit. We're going to invent a new unit. We're going to call it the AMU. And we're going to establish that the atomic mass unit will be something that's a little bit more tractable. So something that we can deal with. And so we'll say that one atomic mass unit is equal to essentially the mass of the proton. So at the order of the significant figure of 1, we'll say that the proton has a mass equal to 1 AMU. So that's a lot easier to deal with than 1.67 or 1.66 times 10 to the negative 27 kilograms. And so that's ultimately why we came up with this unit, is because we, as humans, we typically like to deal with numbers that are really close to 1. So if we just come up with a new relationship, here's the new relationship that we established, then we can now say, all right, we're gonna refer to the masses of these subatomic particles in atomic mass units because they're easier to deal with. And now we'll have some way to sort of to compare them. Okay. So that's it with the proton. Now I want to do the neutron. The neutron And here's a vocabulary word, and I'm not going to define it just yet, but I'm going to underline it. The neutron establishes the particular isotope of the element. And we'll define isotopes starting on Wednesday. But for now, I want to talk about the neutron. When I talk about the proton as identifying the element and by atomic number, right? Because the atomic number equals the number of protons, I mean this. If we go back to helium, we decided that the atomic number was 2. So that means that helium has 2 protons. But there's several different types of helium. I told you about one type that has 2 protons plus 2 neutrons, but there's another type, one that has 2 protons and 1 neutron, and one that has 2 protons and 0 neutrons. All of these things are helium, but they're different isotopes. And so I didn't specifically define isotope, but I am sort of telling you what the word isotope means. And the word isotope has to do with the number of neutrons. And I'll specifically define that when we get together next time. But I want to talk more about neutrons when it comes to what they do for an atom. So the number of protons identifies the atom. The number of neutrons establishes the particular isotope of that element. And it has physical properties in mass that are similar to the proton. So it essentially is the same mass, 1 AMU, but it has no charge. It has 0 charge. Now, what about the electron? What about the electron? Now, we said something about the electron being very small. It has a mass equal to 0.0005 AMU. 0.003 zeros and a 5 in terms of atomic mass units. So that's still really, really, really tiny compared to the mass of a proton. If the proton and neutron is 1 AMU, then this is about, what, 2,000 times smaller in mass than the proton. And we're already saying that protons and neutrons are subatomic particles. So in real life, these particles are incredibly small, and the electron is even 2,000 times smaller than that. The electron has a charge of -1. So the flavor of the charge is negative, and the value of the charge is 1. So now that we've put these 3 things together, let's go back to that picture of helium, and it's going to be the particular version of helium that has 2 neutrons. And let's try to identify the locations. What do we want to call the spot where the neutron and proton are? What's this place called? Just like in a cell, this is going to be the nucleus of the atom. And what we're going to call this, we're going to call where the electrons are located. I'm going to already start to introduce a better word for it. I'm not going to call it an electron orbit. I'm going to call it an electron cloud. And so let me just summarize again where we're at. We've identified the atom, and we've used the model of a little dot to represent what an atom is. And that's okay until we really start to look inside the atom at the subatomic particles. Then we have to use a model that looks like this. And this really is the orbital or the orbit model. And this works for now. And in the orbit model, we have sort of like inside we have a planet and then some moons, like in a regular planetary model. We're going to call this central location where the protons and neutrons reside as the nucleus, and where the electrons are in sort of, remember, they're not really orbiting, but we're going to call these electron orbits, we're going to call them the electron cloud. So where are the electrons? Well, they're in the electron cloud. Where's the electron cloud? It surrounds the nucleus. Where's the nucleus? It's the middle part of the atom. It's definitely not a membrane. It is definitely not a membrane. Okay, and so I want to just leave it there. We're gonna